Our planet, Earth, has been dominating technology since the past centuries, which has continuously growing and expanding up to this day. Numerous changes have occurred, and our curiosity regarding many mysteries and questions has grown over time. Derived by its beauty, Earth is a masterpiece creation created by our own universe. One thing interesting about this pleasing planet is that Earth is not flat, and it is not perfectly round either. Strange but true, it may seem round when viewed from space, but our planet is actually a bumpy spheroid. As countless photos from space can attest, Earth is round. The blue marble, as astronauts have affectionately dubbed it. Appearances, however, can be deceiving. Planet Earth is not, in fact, perfectly round. Why? There have been disagreements throughout history over whether the planet is flat or spherical. The simple answer is that we live on a bumpy, mountainous, cavernous globe. Earth is not a perfect sphere. Its shape is an oblate spheroid. This just means that it flattens at the poles and widens out at the equator. Besides its interesting and deceiving structure, did you know that the continents that exist today was not the same as in the past? 225 million years ago, our planet looked very different. All the continents were joined together in a single supercontinent called Pangaea that existed during the late Paleozoic and early Mesozoic eras. As the plate moved, their supercontinent broke up. New oceans formed as continents drifted around the globe. It is this that has created the shape of the world we know today. The name Pangaea is derived from ancient Greek, all entire or whole, and Gaia or Gaia means Mother Earth or land. The concept that the continents once formed a contiguous landmass was hypothesized, with corroborating evidence by Alfred Wegener, the originator of the scientific theory of continental drift, in his 1912 publication, The Origin of Continents. According to his continental drift theory, all the continents were all joined together in one landmass known as Pangaea, which was surrounded by a single large ocean known as Panthalassa. It is said that the Pangaea was broke into two parts, the Gondwana and Laurasia. These two supercontinents further split into the large land masses which we now know as continents. Wegener originally proposed that the breakup of Pangaea was due to centrifugal forces from the Earth's rotation, acting on the high continents. However, this mechanism was easily shown to be physically implausible, which delayed the acceptance of the Pangaea hypothesis. Arthur Holmes proposed the more plausible mechanism of mantle convection, which, together with evidence provided by the mapping of the ocean floor following the Second World War, led to the development and acceptance of the theory of plate tectonics. Before we continue this prolonged journey, I would like to introduce myself. Hello everyone, my name is Prince Jonah Lisa, the group's leader. Together with my group mates,
Hello everyone, my name is Delkaina Nicole Sigonjaneas, a member from Group 2.
Hello everyone, I am Kelmache Usman, a group member of Group 2.
Hello everyone, my name is Faith B. Deondo, a member of Group 2.
Hello everyone, my name is Franz Allen B. Musico, a member from Group 2.
in today's episode, we will explore the history of Earth with a question stating, What role did plate tectonics play in shaping Earth's landscape? And what information about future geologic events can they tell us now? Tectonic plate movement is the reason why and how Pangaea was formed and divided. Plate tectonics play a crucial role in sustaining life on Earth. The Earth's outermost rigid shell is broken into a series of plates. These tectonic plates drift around moving continents, causing earthquakes and volcanoes, and determining the composition of the air we breathe. The plates are a series of large blocks of rocks that make the Earth's surface appear like a puzzle. The pale blue dot photographed in 1990 by the Voyager 1 from 3.8 billion miles away is in fact the planet Earth. It shows that the Earth is just a speck of dust at the edge of the solar system. Similar pictures have been taken from the surface of Mars and from the Moon as well. But we know that the pale blue dot of planet Earth is special as it sustains life and habitability, although this may not be obvious from such distances. Scientists believe that there are certain signs of life on Earth that can be observed from space. For instance, the Earth's atmosphere has a distinct light spectrum, which indicates that the oxygen and the other gases are present on our planet. The light from Earth also changes with the seasons, meaning the spin axis of the Earth is tilted. Sensitive detectors will determine the length of a day on Earth, as well as find the time between the Earth's full rotations. In what way does the Earth considered as a special planet? What makes the Earth a special planet is because it is the only planet we know that has life. Earth has oxygen, water, and temperature. Water covers 70% of Earth's surface. Earth's atmosphere is made mostly of nitrogen and has plenty of oxygen for us to breathe. The atmosphere also protects us from incoming meteoroids, most of which break up before they can hit the surface. So, what makes the Earth a perfect spot for life? Plate tectonics is one of the key characteristics of Earth that is believed to have played a major role in the evolution of complex life. The influence of plate tectonics on the Earth's climate and carbon cycle, coupled with its role in generating a protected magnetosphere, helped various life forms gain a foothold on the planet. Is Earth the only planet with intelligent life? So, is the Earth really the best planet ever? Scientists believe that the perfect combination of all of these factors, the Earth's placement in the solar system, its oceans, its plate tectonics, its rotation and tilt, and its moon, are what allow intelligent life to grow on our planet. But Earth may not be the only perfect home out there. Despite all of this, there is no geological artist quite like Earth's plate tectonics. Thanks to this ongoing operation, we have mountains and oceans, terrifying earthquakes, incandescent volcanic eruptions, and new land being born every single second.
Now, Have you ever wondered how the Earth started? Earth, the only planet known to maintain life, a product of scientific phenomena and sheer chance. These blue specks in space hold the past, present, and future of our very existence. There are estimated to be more than 100 billion galaxies in the universe. The Milky Way galaxy, our local neighborhood in space, is thought to contain at least 250 billion individual stars. One of these stars is special. The Sun is not an exceptional star in any way. It is not the biggest, or the hottest, or the oldest. What makes it special is that it is the only known star to support a planet that harbors life. Approximately 4.5 billion years ago, the Earth formed from particles left over from the creation of our Sun. Gravity drew these particles together to form pebbles, which then formed boulders and eventually the Earth. At its heart is a solid inner core covered by a liquid outer core. Above this sits the mantle flowing silicate rocks and a rocky crust. This rocky mass is a third planet from the Sun, orbiting the star from an average distance of about 93 million miles. It is close enough to the Sun to be warm, unlike the cold gas giant, but not so close that its surface is exposed to extreme heat and solar radiation as it was the case with Mercury. Earth's unique position in solar systems allows it to house phenomena yet to be found anywhere else in the universe, particularly liquid surface water and life. According to one theory, much of Earth's water is as old as its rocks, both of which having formed during the Earth's earliest days. Because of Earth's unique distance from the Sun, the planet is able to contain water in all of its form, liquid, ice, and gas, rather than having them permanently frozen or evaporated into space. But Earth is the only known place in the universe with the liquid water on the surface, thereby having unique cascading effect on the planet. It hydrates the land, helping create nutrient-rich soil. It collects and pulls to form ocean and freshwater system. And it cycles upward to add moisture to Earth's protective atmosphere. And where there is liquid water, there is life. About 3.8 billion years ago in Earth's ocean, primitive life exists in a form of microbial organism. They and the ensuing billions of years gave rise to a range of more advanced life form that thrives in Earth's seas, land, and skies. Earth's development has started with evolution. It is composed of eons and is consists of different eras and periods, which develop over time by the Earth's origin of interval time. The first eon form was Hadean Eon. Hadean Eon, informal division of Precambrian time occurring between about 4.6 billion and about 4 billion years ago. During Hadean time, the solar system was forming, probably within a large cloud of gas and dust around the Sun, called an accretion disk. The relative abundance of heavier elements in the solar system suggests that this gas and dust was derived from supernova or supernovas, the explosion of an old massive star. Throughout part of the aeon, impact from extraterrestrial body release enormous amount of heat that likely prevent much of the rock from solidifying at the surface. As such, the name of the interval is a reference to Hades, a Greek translation of the Hebrew word for hell. Earth's surface was incredibly unstable during the early part of the Hadean Aeon. Convection current in the mantle brought molten rocks to the surface and caused cooling rocks to descend into magmatic seas. Heavier elements such as iron descended to become the core, whereas lighter elements such as silicon rose and become incorporated into a growing crust. Although no one knows when the first outer crust of the planet formed, some scientists believe that the existence of the pure grain of zircon dated to about 4.4 billion years ago, confirmed by the presence of stable continent, liquid water, and surface temperature that were probably less than 100 Celsius or 212 Fahrenheit. Since Hadean times, nearly all of this original crust had subtracted from the movements of tectonic plates, and thus pure rocks and minerals remains from the interval. The oldest rocks known are the Po-amphibolite volcanic deposit of the Nubugatuk Greenstone Belt in the Quebec, Canada. They are estimated to be 4.28 billion years old. The oldest minerals are the aforementioned grain of zircon, which were found in the Jack Hills of Australia. The second aeon formed was Archean Aeon. Archean Aeon, also spelled Archean Aeon, the earlier of the two formal divisions of Precambrian time, about 4.6 billion to 541 million years ago, and the period when life first formed on Earth. The Archean Aeon began about 4 billion years ago with the formation of Earth's crust and extended to the start of Proterozoic Aeon 2.5 billion years ago. The latter is the second formal division of Precambrian time. It was preceded by the Hadean Aeon, an informal division of geologic time spanning from about 4.6 billion to 4 billion years ago, and characterized by Earth's initial formation. Records of Earth's primitive atmosphere and oceans emerged in the earliest Archean era. Fossils evidence of the earliest primitive life forms, prokaryotic microbes of the domain called Archaea and bacteria appears in rocks about 3.5 to 3.7 billion years old. However, the presence of the ancient fragments of graphites, which may have been produced by microbes, suggests that life could have emerged sometimes before 3.95 billion years ago. Archean greenstone granite belts contain many economic minerals deposits, including golds and silvers. During the Archean Aeon, methane droplets in the air shrouded the young Earth in a global haze. There was no oxygen gas on Earth. Oxygen was only in compounds such as water. Complex chemical reaction in the young ocean transformed carbon-containing molecules into simple living cells that do not need oxygen to live. What life existed in Archean? Life in Archean was limited to simple single-cell organisms lacking nuclei, called prokaryotes. In addition to the domain bacteria, microfossils of the domain Archaea have also been identified. When did life first appear on Earth? The earliest life form we know were microscopic organisms, microbes, that left signals of their presence in rocks about 3.7 billion years old. The signal consisted of a type of carbon molecule that is produced by living things. The third eon that was formed was the Proterozoic eon. The Proterozoic is a geological eon spanning the time interval from 2500 to 538.8 million years ago. It is the most recent part of the Precambrian supereon. During the Proterozoic eon, modern plate tectonics became active, and the ancient cores of the continent moved over wide area of the globe, accumulating smaller fragments of crust and sometimes colliding with other large land masses. The opposite also happens, leading to continental drifting. Proterozoic rock had been identified on all the continents and often constitute important sources of metallic ores, notably of iron, gold, copper, uranium, and nickel. During the Proterozoic, the atmosphere and ocean changed significantly. Proterozoic rock contains many definite traces of primitive life forms. The fossil remains of bacteria and blue-green algae as well as the first oxygen-dependent animal, the Ediacara fauna. Oxygen is a byproduct of photosynthesis. Free oxygen in the atmosphere increased significantly as a result of biological activity during the Proterozoic. The most important period of the change occurred between 2.3 billion and 1.8 billion years ago when free oxygen began to accumulate in the atmosphere. The last eon was Phanerozoic eon. Phanerozoic eon, the span of geologic time extending about 541 million years from the end of the Proterozoic eon, which began about 2.5 billion years ago to the present. The Phanerozoic, the eon of visible life, is divided into three major spans of time largely on the basis of characteristic assemblage of life forms. The Paleozoic, 541 million to 252 million years ago. Mesozoic, 252 million to 66 million years ago. And Cenozoic, 66 million years ago to the present eras. Although life clearly originated at some time, probably quite early, in the Archean Eon, which lasted from 4 billion to 2.5 billion years ago. Not until Phanerozoic did a rapid expansion and evolution of forms occur and fill the various ecological niches available. During the Phanerozoic, Earth gradually assumed its present configuration and physical features through a process as continental drift, mountain building, and continental glaciation. Thus, although the Phanerozoic eon represents only about the last 1/8 of time since Earth's crust formed, its importance far exceeds its relatively short duration.
Under the Phanerozoic Aeon, it is composed of era. The first era is Paleozoic era. Paleozoic is 541 to 252 million years ago, means Asian life. The oldest animals on Earth appeared just before the start of this era, in Ediacaran period, but scientists have not yet discovered then what the geologic timescale was made. Thus, 7th Paleozoic era is made out of 7 periods. The first one is the Cambrian period, The Cambrian period marks an important point in the history life on Earth. This is the time where many kinds of invertebrates and the first vertebrate fishes appeared in the fossil record. This event is sometimes called the Cambrian explosion because of the relatively short time over which this density of forms appears. It was once thought that Cambrian rocks contain the first and oldest fossil animals, but these are now found in the early Ediacaran or Vendian strata. Number 2 is the Ordovician period. Ordovician period in geologic time, the second period of the Paleozoic era. It began 485.4 million years ago, following the Cambrian period, and ended 443.8 million years ago. The Silurian period began when Ordovician rocks have the distinction of occurring at the highest elevation on Earth, the top of Mount Everest. The Ordovician is best known of its diverse marine invertebrates, including graptolites, trilobites, brachiopods, and conodots, early vertebrates. A typical marine community consisted of these animals, plus red and green algae, primitive fish, cephalopods, corals, crinoids, and gastropods. The number 3 is the Silurian period. Silurian period in geologic time, the third period of the Paleozoic era. It began 443.8 million years ago and ended 419.2 million years ago. Extended from the close of the Ordovician period to the beginning of the Devonian period. During the Silurians, continent elevation were generally much lower than in the present days, and global sea levels was much higher. Sea levels rose dramatically as the extensive glaciers from the late Ordovician Ice Age melted. This rising prompted changes in the climatic conditions that allowed many faunal groups to recover from the extinctions of late Ordovician times. Large expanses of several continents become flooded with shallow seas, and mound-type coral reefs were very common. Fishes were widespread. Vascular plants began to colonize coastal lowlands during the Silurian period, whereas continental interior remains essential barren of life. The fourth is Devonian period. Devonian period in geologic time, an interval of the Paleozoic era that follows the Silurian period and precedes the Carboniferous period, spanning between about 419.2 million and 358.9 million years ago. The Devonian period is sometimes called the Age of Fishes because of the diverse, abundant, and in some cases, bizarre types of these creatures that swarm Devonian seas, forests, and the coiled shell-bearing marine organisms known as ammonites first appeared in the Devonian. Late in the period, the four-legged amphibians appeared, indicating the colonization of land by vertebrates. During most of the Devonian period, North America, Greenland, and Europe were united into a single northern hemisphere landmass, a minor supercontinent called Eurasia or Euramerica. The union of the paleocontinents of Laurasia, comprising much of North America, Greenland, Northwest Ireland, Scotland, and Jutok peninsula of northeastern Russia, and Baltica, now most of northern Europe and Scandinavia, occurred near the beginning of the Devonian period. Intensive terrestrial deposits known as the Old Red Sandstone covered much of its northern area, while widespread marine deposits accumulated on its southern proportions. The Paleoequator, the site of the equator at the point in the geologic pass, passed through North America and through China, in which at that time a separate landmass South America, Africa, India, Australia, and Antarctica were joined into the southern hemisphere continent of Gondwana. Parts of these continents were also often covered by sea water. The fifth is Mississippian period. Mississippian subperiod, first major subdivision of the Carboniferous period, lasting from 358.9 to 323.2 million years ago. The Mississippian is characterized by shallow water limestone deposits occupying the interiors of continents, especially in northern hemisphere. This limestone exhibits a charge from calcite dominated grains and cements to aragonite dominated ones. This change is reflective of an increase in the ratio of magnesium to calcium in seawater. Due to the decreased rates of seafloor spreading, during this time, sea level began a cyclic retreat from the continental interiors that would end in a worldwide low stand at Mississippian to Pennsylvanian boundary. The Mississippian subperiod is also recognized as the interval in which armored fishes, plentiful during the Devonian period, 419.2 to 358.9 million years ago, went largely extinct. Number 6 is the Pennsylvanian period. The Pennsylvanian period, second major of interval of the Carboniferous period, lasting from 323.2 million to 298.9 million years ago. The Pennsylvanian is recognized as a type of significant advance and retreat by shallow seas. Many non-marine areas near the equator became coal swamps during the Pennsylvanian. These areas are mined for coal today. Number 7 is Permian period. Permian period in geologic time, the last period of the Paleozoic era. The Permian period began 298.9 million years ago and ended 252.2 million years ago, extending from the close of the Carboniferous period to the outset of the Triassic period. At the beginning of the period, glaciation was widespread and latitude climatic belts were strongly developed. Climates warmed throughout the Permian times, and by the end of the period, hot and dry conditions were so extensive that they caused a crisis in Permian marine and terrestrial life. This dramatic climatic shift may have been partially triggered by the assembly of smaller continents into the supercontinent of Pangaea. Most of Earth's landmass was incorporated into Pangaea, which was surrounded by immense world ocean called Panthalassa.
The next era under Phanerozoic era is Mesozoic era. Mesozoic era, 252 to 66 million years ago, means the middle life, and this is the time of the dinosaurs. This era includes the Jurassic, Jurassic, and Cretaceous periods, names that may be familiar to you. The Mesozoic era is also called Age of Reptiles and the Age of Conifers. It's the second to last era of Earth geological history, lasting from about 252 to 66 million years ago, and comprising the Jurassic, Jurassic, and Cretaceous periods. Mesozoic era is divided into three periods. First, Jurassic period. Jurassic period in geologic time, the first period of Mesozoic era, it began 252 million years ago at the close of Permian period and ended 201 million years ago, when it was succeeded by Jurassic period. During the Jurassic, the first dinosaur walked on the land, the first Pterosaurus sailed through the sky, and the first Ichthyosaurus and Plesiosaurus swam in the ocean. The lineage of many modern-day reptiles began in the Jurassic period, including crocodiles, lizards, and turtles. The Triassic period marked the beginning of the major changes that were to take place throughout the Mesozoic era, particularly in the distribution of continents, the evolution of life, and the geographic distribution of the living things. At the beginning of Triassic, virtually all the major land masses of the world were collected in the supercontinent of Pangaea. Terrestrial climates were predominantly warm and dry, though seasonal monsoon occurred over large areas, and the earth crust was relatively quiescent. At the end of Triassic, however, plate tectonic activity picked up, and a period of continental rifting began. On the margins of the continental's shallow seas, which had dwindled in the area at the end of Permian, became more extensive as sea level gradually rose. The water continental shelves were colonized for the first time by large marine reptiles and reef-building corals of modern aspect. This followed on the heels of the large mass extinction in the history of the Earth. This event occurred at the end of Permian, when 85 to 95% of marine invertebrate species and 70% of terrestrial vertebrate genera died out. During the recovery of the life in the Triassic period, the relative importance of the land animals grew. Reptiles increased in the diversity and number, and the first dinosaurs appeared, heralding the great radiation that would characterize this group during Jurassic and Cretaceous period. Finally, the end of the Jurassic saw the appearance of the first mammals, tiny, fur-bearing, shell-like animals derived from reptiles. Second, Jurassic period. The Jurassic is geologic period and stratigraphic system that spanned from the end of the Jurassic period 201.3 million years ago to the beginning of the Cretaceous period, approximately 145 million years ago, the Jurassic period existed from 199.6 million to 145.5 million years ago. It was characterized by a warm, wet climate that gave rise to lush vegetation and abundant life. Many new dinosaurs emerged in great numbers. Among them were Stegosaurus, Brachiosaurus, Allosaurus, and many others. The cause of extinction is unknown, but there is somewhat speculation that it was triggered by release of huge methane deposit from within the earth. This deposit formed beneath the seabed as surface algae dies and sink to the sea floor. Third, Cretaceous period. Cretaceous period, in geologic time, the last of the three periods of Mesozoic era. The Cretaceous began 145 million years ago and ended 66 million years ago. It followed the Jurassic period and was succeeded by the Paleogene period, the first of the two periods into which the Tertiary period was divided. The Cretaceous is the longest period of the Phanerozoic eon, spanning 79 million years. It represents more time than has elapsed since the extinction of the dinosaurs, which occurred at the end of the period. The Cretaceous period. The Cretaceous is usually noted for the being the last of portion of the age of dinosaurs, but that doesn't mean that new kinds of dinosaurs did not appear then. It is during the Cretaceous that were the first Ceratopsian and Pachycelosaurus dinosaurs appeared.
The last era under the Phanerozoic era is Cenozoic era. Cenozoic era, third of the major eras of Earth's history, beginning about 66 million years ago and extending to the present. It was the interval of time during which the continents assumed their modern configuration and geographic positions, and during which Earth's flora and fauna evolved toward those of the present. The Cenozoic is Earth's current geological era, representing the last 66 million years of Earth's history. It is characterized by the dominance of mammals, birds, and flowering plants, a cooling and drying climate, and the current configuration of continents. From the extinction of dinosaurs until today, the Cenozoic era is the age of mammals. Mass extinctions create opportunities for new life to thrive, and mammals fill the gap that the dinosaurs left behind. They evolved into many species you would recognize today, including humans. The Cenozoic era is generally divided into three periods. The first period is the Paleogene, 66 million to 23 million years ago. The second one is the Neogene, 23 million to 2.6 million years ago. And the last one is the Quaternary, 2.6 million years ago to the present. However, the era has been traditionally divided into the Tertiary and Quaternary periods. The designations Tertiary and Quaternary, however, are relics of early attempts in the late 18th century at formulating a stratigraphic classification that included the now wholly obsolete terms primary and secondary. In 1856, Austrian geologist Moritz Horns introduced the terms Paleogene and Neogene, the latter encompassing rocks equivalent to those described by Scottish geologist Charles Lyell as Miocene and older and newer Pliocene, which included what he later called the Pleistocene. Today, in our modern civilization, We live in Holocene epoch of the Quaternary period. This period is also referred as the Great Acceleration. Carbon dioxide emissions, global warming, ocean acidification, habitat destruction, extinction and wide-scale natural resource extraction are all signs that we have significantly modified our planet. Furthermore, our ways of life have evolved as a result of the continual growth of our technologies, which has made a significant contribution to our human capacities in all ages. It is true that our modern society has seen a brave and a significant transformation, but this does not affect the reality that the world is still continually living under the provisions of our science. Since the Pangea, along with other periods of ongoing development, the world has grown in size. In today's society, there are some questions that might be seen as legitimate. What might Earth's next supercontinent look like? Over geologic timescales, Earth's continents continually change. Geologists believe that every few hundred million years, the continents combine to create massive supercontinents. The most famous past supercontinent is probably the most recent one, Pangaea. This article on future supercontinents was originally published November 27, 2018. The last supercontinent, Pangaea, formed around 310 million years ago, and it started breaking up around 180 million years ago. It has been suggested that the next supercontinent will form in 200 to 250 million years, so we are currently about halfway through the scattered phase of the current supercontinent cycle.
How will the next supercontinent form and why? There are four fundamental scenarios for the formation of the next supercontinent. They are Novo Pangea, Pangea Ultima, Aurica, and Amasia. How each forms depend on different scenarios, but ultimately are linked to how Pangea was separated and how the world's continents are still moving today. The first supercontinent might form in the future is number 1, Novo Pangea. If we assume that present-day conditions persist so that the Atlantic continues to open and the Pacific keeps closing, we have a scenario where the next supercontinents form in the antipodes of Pangea. The Americas would collide with the northward drifting Antarctica and then into the already collided Africa-Eurasia. The supercontinent that would then form has been named Novo Pangea or Novo Pangea. There, the old ocean floor is recycled and can go into volcanic plumes. The Atlantic, by contrast, has a large ocean ridge producing new ocean plate, but is only home to two subduction zones, the Lesser Antilles Arc in the Caribbean and the Scotia Arc between South America and Antarctica. The second one is Pangea Ultima. The Atlantic opening may slow down and actually start closing in the future. The two small arcs of subduction in Atlantic could potentially spread all along the east coast of Americas, leading to a reforming of Pangea as the Americas, Europe, and Africa are brought back together in a supercontinent called Pangea Ultima. This new supercontinent would be surrounded by a super Pacific Ocean. Number 3 is Aurica. However, if the Atlantic was to develop new subduction zones, something that may already be happening, both the Pacific and Atlantic Oceans may be fated to close. This means that a new ocean basin would have to form to replace them. In this scenario, the Pan-Asia Rift currently cutting through Asia from west of India up to the Arctic opens to form the new ocean. The result is the formation of the supercontinent Aurica. Because of Australia's current northwards drift, it would be at the center of the new continent, as is Asia and the Americas close to the Pacific from either side. The European and African plates would then rejoin the Americas as the Atlantic closes. Number 4 is Amasia. The fourth scenario predicts a completely different fate for future Earth. Several of the tectonic plates are currently moving north, including both Africa and Australia. This drift is believed to be driven by anomalies left by Pangaea, deep in the Earth's interior, in the part called the mantle. Because of this northern drift, one can envisage a scenario where the continents, except Antarctica, keep drifting north. This means that they would eventually gather around the North Pole in a supercontinent called Amasia. In this scenario, both the Atlantic and the Pacific would mostly remain open. Investigating the Earth's tectonic future forces us to push the boundaries of our knowledge and to think about the processes that shape our planet over long time scales. It also leads us to think about the Earth's system as a whole and raises a series of other questions. What will the climate of the next supercontinent be? How will the ocean circulation adjust? How will life evolve and adapt? These are the kind of questions that push the boundaries of science, further because they push the boundaries of our imagination. What possible supercontinents might form according to scientists? The Arctic Ocean and Caribbean Sea will vanish in the next 200 to 300 million years, and Asia will collide with the Americas to form a new supercontinent named Amasia, according to scientists. The Pacific Ocean is reportedly receding by almost an inch a year, according to researchers at Curtin University in Australia and Peking University in China. They therefore think that the Americas and Asia will eventually collide to form a new supercontinent called Amasia at some point in the future, perhaps within 200 million to 300 million years, when the Earth's land masses will join together. Over the past 2 billion years, Earth's continental have collided together to form a supercontinent every 600 million years, known as the supercontinent cycle. This means that the supercontinents are due to come together again in a couple of hundred of millions of years, said Dr. Chuan Huang, lead author of a study published in the journal National Science Review. Currently, Earth consists of 7 continents with widely different ecosystems and human cultures, so it would be fascinating to think what the world might look like in 200 million to 300 million years, they said. How did geologists predict the supercontinent? Scientists say that the Pacific Ocean, the world's oldest ocean, is shrinking about 1 inch per year. In a mere 200 to 300 million years, they claim that the North America will collide with Asia, giving us the new supercontinent called Amasia. Researchers have long held theories about what is known as the supercontinent cycle. Over the past billions of years, Earth's continents have collided together roughly every 600 million years and then broken apart again, giving us the past supercontinents like Columbia, Rodiana, and Pangaea. Now, scientists and Curtin universities in Australia posit that our next supercontinent cycle will occur due to the closing of the Pacific Ocean. By simulating how the Earth's tectonic plates are expected to evolve using a supercomputer, we were able to show that in less than 300 million years, it is likely to be the Pacific Ocean that will close, allowing for the formation of Amasia. Will humans still sustain life in the upcoming supercontinent? According to geologists, human species will probably be long gone by then, so we don't know. But it is certainly fun to think about. If we were to think about that we still live in that era, there is a possibility that we might not or can't sustain life in the upcoming supercontinent because of the danger that poses, just as in our modern society. There has been a lot of problems that has not been solved yet, and so these problems will also become a threat to the future generation. So the conclusion of this answer is that there are two possibilities. There might be or not. There has been so much presence and changes happened that caused the origin of our Earth. There's theories, possibilities, and of course, mysteries. But on a certain level, only science will tell the fate of our very existence. Hello everyone, once again I am Prince Jonah Pilisa, the leader of Group 2. Along with my group members,
Jelkaina Nicole Sigondraneos.
Franz Allen B. Musico.
My name is Faith B. Deondo.
Mancho Eden Usman.
and this is our performance task in science. I hope you learned something new and had fun. Thank you for watching!